Now let's do part B. Part B. Find the average velocity of the particle for the time period between time 0 and time 6. So the easy way to think about this, average velocity, is that your average, or one way to think about it, the distance that you travel, sometimes I use d for distance, or you could use s for sometimes for displacements used, but your distance in general is equal to your average velocity times time, or your average velocity is equal to the distance you travel divided by time. And so how do we figure out the distance that we travel over that period, especially because they didn't explicitly give us the position function? Well, if you think about it, let's think about the velocity function right over here, which they did give us, v of t. And I don't know exactly what it looks like, but let me just draw a general velocity function right over here. And we care, so this is our t-axis, and this is our velocity axis right over here. And we care about between time 0 and time 6. And let's say our function does something like this. It doesn't really matter. This is just a general drawing over here. How do we figure out the total distance over that time? Well, if you take any small time right over here and you multiply it times the roughly constant velocity over that time period, then that will tell you the area of this little column will tell you approximately the distance traveled over this very small interval of time, because you have a time for time times an approximately constant velocity will give you a distance. And so in general, if you take the area under this curve, from 0 to 6, that will give you the total distance traveled. So d is equal to the definite integral from 0 to 6 of v of t, of this thing right over here, v of t dt. And so if you want the average velocity, you just find the distance, which is this definite integral, and then you divide that by the time, or the elapsed time. And the elapsed time in this case, I could actually write times delta t right over here. Our change in time right over here is going to be 6. We start at 0 and we finish at 6. So we just have to evaluate this definite integral, which is not that easy to evaluate analytically. And it's lucky for us that they do allow us to use calculators in this part. So we'll evaluate it using the calculator, and then we just have to divide it by 6. So let's first find out the distance traveled between time 0 and time 6. And to do that, we can use the TI-85. We'll go to catalog. This tells us all of the different functions they have. And to evaluate definite integrals, we use so I'll just go straight to the F. This, go one page down. So this right here, fn int. So this is definite integrals. So I'll use fn int. You could just type that in, but this way we know we got the case right and everything. So the definite integral of, and instead of I'll put v of t here, but I'll write it as v of x just because x is an easier key to get to. So we want to take the definite integral of 2 sine of e to the t over 4. So let me put another parentheses here. So it's 2 times the sine of e to the t over 4. Well, I'll just write x over 4. I'll write x instead of t just because it's an easier key to get to. And I'll tell the calculator that we're integrating with respect to x and not t. X divided by 4. X divided by 4. Let me close that parentheses. And then let me close that parentheses. That closes this parentheses. Now I want to close this parentheses right over there. And then I have a plus 1. So that is our velocity function expressed as a function of x. And now I'll say that the variable of integration that we're integrating with respect to is x. I could have put t there, and that would have been fine. And then our bounds are from 0 to 6. From 0 to 6. And if I haven't made a mistake with the parentheses, this should evaluate to something. So what does it evaluate to? The TI-85 is just chugging away. 11.696. So this is equal to, this right over here is 11.696. So the total distance traveled is 11.696. Our change in time is 6, so we just have to divide this by that. We have to divide the total distance divided by the change in time. And so we just take the total distance and we divide it by, this is just our previous answer, divided by our change in time. So it's 1.949. So our average velocity is equal to 1.949 949. And we don't know the units. They didn't give us any units here. So that's part B. Now let's do part C. Part C. Find the total distance traveled by the particle from time t equals 0 to t equals 6. Well, lucky for us, we actually figured that out as part of part B. We figured that out. It was 11.696. So we just have to write that down, 11.696. And then finally we're on part D. Part D, and I'll do this in this blue color. Part D. For t between 0 and 6, the particle changes direction exactly once. Find the position of the particle at that time. So let's think about the time when the particle changes direction, and then we'll have to figure out how we can evaluate its position, or how we can figure out its position at that time. So if the particle changes direction, that means that the velocity is going from either a positive velocity to a negative velocity, or a negative velocity to a positive velocity. It's switching direction. So if that would be a point, so if this is, let me draw it. So this is our time axis, and this is our velocity axis. It must be a point in time. So we're switching direction. So if our velocity function looks like something like that, then this would be a point in time when we're switching direction. We're going from a positive velocity to a negative velocity, or it could be something like this. We're going from a negative velocity to a positive velocity. But the bottom line, it's a point where the velocity hits 0, and then on either side of that we have kind of switched signs. It wouldn't be a point like this where it's just going from positive to 0 and then positive again. This would kind of be something that's just going in the same direction after pausing. So let's figure out where between 0 and 6 our velocity function is equal to 0. And if we have, and they're telling us that the particle changes direction exactly once. So if we find the 0 of the velocity function, they already tell us that the particle changes direction. You could test it on either side to make sure that it's changing direction, but it's probably a pretty safe bet that if you find the 0, that will be the time when you've changed direction. So we essentially just have to figure out when the velocity is equal to 0 here. So the velocity function is 2 sine of e to the t over 4 plus 1. And we want to set this equal to, we want to find out when this equals 0. And we want to get a time that's between 0 and 6. And so we can subtract 1 from both sides. You get 2 sine of e to the t over 4 is equal to -1. We can divide both sides by 2. You have sine of e to the t over 4 is equal to -1/2. And we can use a calculator here, or we could just think about it a little bit in terms of the unit circle, which I always like to do. If you're short on time, you might want to use your calculator. But the unit circle, since you know exactly what you're doing when you're taking the inverse sine, it's a little bit more useful, because there's obviously multiple angles right over here that you could put in here that would give you a sine of 1/2. And you want to make sure that whatever answer you get, it gives you a t that's in that interval that we care about. So let's think about the unit circle. If the sine of something is -1/2, there's 2 points on the unit circle where the sine is equal to -1/2. It's right over here, where the sine is equal to -1/2, and you could view this angle right over here, -1/2. You could view this as negative pi over 6, or you could view this as 2 pi minus pi over 6, if you want to view it going all the way around there. And then the other point on the unit circle where you are at, where the sine is -1/2, is right over here. And so to get over there, we would have gone pi first. You go pi, and then you'll go another pi over 6. So this angle right over here is pi plus pi over 6, which is equal to 6 pi plus pi over 6, or 7 pi over 6. 7 pi over 6. This angle right over here, this would be 11 pi over 6. You take 2 pi minus pi over 6 if you wanted to go all the way around there. And then you can continue to add 2 pi to either one of these to get multiple angles where the sine of that angle is equal to -1/2. But let's just try this over here. Let's just go with this first angle, this kind of the first angle that gives us a sine of -1/2, and see if when we solve for t, we get a t that's in our interval. So we could say, if sine of this business over here is equal to -1/2, then this business in here, then e to the t over 4 could be equal to 7 pi over 6. Could be equal to 7 pi over 6, based on the logic we just did over here. And then, to solve for t, we could take the natural log of both sides. So we could say that t over 4 is equal to the natural log of 7 pi over 6, or that t is equal to 4 times the natural log of 7 pi over 6. So hopefully this gives us a t that's inside of our interval. So let's try this out. So if we want to multiply 4 times the natural log of 7 pi divided by 6. So let's see what we get. We get 5.19. So lucky for us, it is in our interval. So this is the t that matters. So 5.196, I'll say. So this is equal to 5.196 approximately. So that's the t where it changes direction. But that's not just what they're asking us. So the particle changes direction exactly once. Find the position of the particle at that time. So this is interesting because they haven't explicitly given us the position function. But we know that the position function is really just the integral of the velocity function. We know that the position function x of t is just going to be the integral from 0 to t of v of t dt plus some constant. And they give us that initial condition. They tell us that x of 0 is equal to 2. They told us that over here, x of 0 is equal to 2. So we actually know what the constant is, because if you evaluate this as x of 0, you get x of 0 is equal to the integral from 0 to 0 of v of t dt plus c, and this is going to be equal to 2. Well, this part right over here evaluates to 0, so we know that our constant is equal to 2. So we know that x of t is equal to the definite integral from 0 to t of v of t dt plus 2. And you might say, well, how do we know the position if we get at a given time? Well, we luckily have a calculator that can calculate definite integrals quite well. So if we want our position at 5.196 seconds, we just have to take the definite integral from 0 to 5.196 of our velocity function and add 2 to that. And so let's get the calculator back out and let's actually calculate that. So once again, let's go to our catalog of functions. I want to go down to the f's, so I'll go down to the f's. I'll go down one more page. No, I didn't want to go down. Go up a page. No, down 2 pages actually. So one more. Okay, so there we go. This is my definite integral function, and I want to take the definite integral of our velocity function. So let me get it. The velocity function, I don't have it written over here. Actually, we've already done it up here. This was our velocity function, so let me write it again. So the velocity function was 2 times the sine of e to the, and I'll just use x as my variable of integration, x divided by 4, close one parenthesis, close another parenthesis, that gets us there, and I want to close that one, and then I want to do a plus 1, right over there, and then I want to say my variable of integration is x, and I'm taking the integral from 0, instead of from 0 to 6, I'm taking the integral from 0 to 5.196, or actually it was my previous answer, so I can just say my previous answer, and so now this will evaluate my definite integral. It'll evaluate this first part right over here, and then I just have to add 2 to it. I have to add 2, so let's add 2, and I'll get my answer. Let the calculator think about it for a little bit. And then voila, 14.134. So our final position is equal to 14.134 if I round it off a little bit.